Alright, so we're going to finish this problem. Apologize for that. I was having some issues with the audio and want to make sure it was working. So find the equation of the line of intersection, and specifically the parametric equations representing that. Alright, so first, what is the equation of a line? The vector form of that is r is equal to r naught plus tv. And so this is really helpful because the ingredients we need here is r naught and v. We need to find those things. And so recall that r naught, or r sub 0, is basically a point on the line. And it can be any point. So, and then you just write it as a vector, and that would be the vector that starts at the origin and goes to that point. So we're going to start there actually, and in the notes I had you do some steps of your own, and maybe they're a little different than this, so that's fine. First of all, we're going to find that point. So remember, this is on the line of intersection between the two planes. And so what your book does, and I like this method, is just let one of the variables, specifically z, equal 0, and then find the x and the y that correspond with that. And so that's one point out of a lot on that line, but setting one of those variables equal to 0 is handy because it makes the other ones easier to find. So I'm going to let equal 0, z equals 0 in each of the equations of the planes, and then notice that x and y will remain. I'm scrolling here so I can grab these equations of the plane. Oops, I don't know if that actually worked. Let's try that again. Okay. So I'll throw those down here. And I'll just describe this a little bit more completely up here. Then we're going to have two equations with x and y. Then we're going to solve that system for x and y, and then that gives us our point. So letting again z equals 0, what we're going to have is 3x minus 2y equals 1 for the first plane, and we'll have 2x plus y equals 3 for the second one. So there's our system. You can solve that any way you want. I think the way I'm going to solve it is with substitution, because the second equation is really easy to solve for y. And then I'm going to sub in 3 minus 2x for y. Do that below here, 3x minus 2 parentheses 3 minus 2x is equal to 1. And then go ahead and distribute. Here we get 3x minus 6 plus 4x equals 1. So 7x minus 6 equals 1. And so we're going to get x equals 1. We got that ready-made equation for y, so we're going to go ahead and sub in there. And we get 1 for that one as well. So our point is 1, 1, 0. Now we're on to the next part where we need to find that directional vector v in order to plug into our equation of the line. So keeping in mind that we're talking specifically about an intersection of two planes, we need to have a bit of information about how we find this directional vector. It turns out a good way to do that is to note that the cross product of the normal vectors to the plane will be a directional vector you can use. So remember that the cross product in general for two vectors gives you another vector that's orthogonal or perpendicular to those two vectors. And so I'm not going to talk about the details here, but that was in the notes, and there's a figure kind of showing that. So we're going to take that for granted right now, and we're going to do this calculation. So the normal vectors are off the page right now, but I will copy them down for you. They were 3, -2, 1, and 2, 1, -3. Alright, so different ways to find the cross product. First of all, it's different than the dot product, a little bit more involved. I'm going to do this determinant style with a matrix. I have my ijk unit vector, then I write 3, -2, 1, then next I write 2, 1, -3, and I want to find the determinant of that. So if we do this covering, you can get some 2x2 matrices that we find the determinant of them. So for the I, you cover underneath the I, which would be the 3 and the 2, and then you take this part as your 2x2. And I'll undo that because I don't want to get that really messy. So just a reminder that -2, 1, 1, -3 for the I component. We need, and again, that notation means we need to find the determinant of that. And then here's a detail that I forget sometimes, and that's making sure that you write it as minus here. The rest are positive, but this j component is negative. So from here we have, covering underneath the j, we would have 3, 1, 2, -3. And then finally plus covering under the k, we get the matrix 3, -2, 2, 1. Alright, so finding the 2x2 determinant, we take -2, diagonally multiply by -3, then it's minus between these always, and then I'm starting up here at the top right corner and moving diagonally to the other corner, and I have 1 times 1 from that. Don't forget the negative for the j component, and we have 3 times -3 minus 1 times 2, and then finally with the k, we're going to have 3 times 1 minus -2 times 2. So doing these calculations, we're going to get 6 minus 1, that's 5. Then we're going to get -9 minus 2. It's -11 times the negative is 11. And then we get 3 plus 4, which will be 7. So that is a normal vector, or excuse me, that is a vector that we can use for the directional vector of the line of intersection. And we found that from the cross product of the normal vectors of the planes. So now finally we are on to the last step, which I'll call step 3. And going back to this equation of a line, we just need to plug our stuff into that and write it in parametric form. So r is x, y, z, written out in components, and then r sub naught was the point, which we're writing out as a vector, 1, 1, 0, and then plus, we have the parameter t, and then our directional vector v is 5, 11, 7 that we just found, and finally now we can write this out. So x is equal to, we'll have 5t plus 1, then we have y is equal to, and we'll have 11t plus 1, and the last component, z, will be simply 7t because we have the plus 0 there. And now we are done with this problem.